stage that there's a relation between the signal speed and the geometry. Where in your life do you also observe that? Is anybody playing an instrument? So what is the relation between geometry and wavelength?
The bigger the instrument, the deeper is the sound or wavelength gets bigger.
Yeah, that is one finding. Very correct. So that means that so it's very obvious to you that, for example, if you combine anything which has cello, contrabass, and so on, that the bigger instrument has the deeper sound. That's one thing. And there's a second finding also that there's a resonance. Yeah, so an instrument is not only emitting one particular wavelength, but especially for music instrument, there's also not only the extension in one direction, but also a side direction, which also makes some kind of sound. So that's also important. Yeah? So this idea is important. So that means that such a structure is also in a way doing something for us. For example, being a filter. You could say it's emitting a certain wavelength, the contrabass or the cello or the violin. But you could also say they don't emit the other ones, which is the same. And this is important for memory, for example, because when you transport data into that, you may hit such resonances, and then something like a memory would not work, because you cannot get a certain amount of speed into this device because it has a filter function. So you cannot disregard this point, yeah, because you cannot really tell a memory, don't use this particular signal. That would be quite strange. Yeah? So there's some learning in this. The point about frequency usage, when we are going back to the generic microwave idea, is a bit more delicate. That is that when we are going up in frequencies, we are not free. Yeah? So there's a historical and a very historical, colorful distribution of frequencies assigned to applications. And for example, the reason why we are using microwaves at 2.4 gigahertz, the ovens, is simply because this band is freed for this kitchen use. Yeah? There's not a particular reason why we couldn't do this at another frequency, except that we do something strange, like emitting a very high power at this frequency. Yeah? By the way, what is protecting you in the microwave oven from this high power? Why are you not fried when you're standing in front of that?
The metal inside the oven.
And so on the back it's very clear. What is on the glass side when you watch the pizza or the vegetables turning? What is there? What is protecting you there? Does anybody know? Maybe this is some homework. You go to your microwave oven and you will see, as you said, it's a grid of metals. So it's not just pure glass. If it was pure glass, you would just get the full power out. And that would be not healthy. It would maybe even harm me. Yeah? So we are not allowed to emit the power which the microwave oven is able to provide. So it's 1,000 watts. If we turned that on and put it here to the spectrum, you would have a very strong reaction from the local authorities. So if you emitted that, and the reason is there's a window, and this is, as you say, small holes which are adjusted that in a way that the microwaves are not transpiring through the glass. You can still look through that because you see that obviously all of us have a feeling for a pizza turning. Yeah? And along with the frequency allocation, we have a maximum level of power which we are allowed to use. And maybe this is also a take-home message. If you ever work in medical applications or in the industry, if you use in a sensor industry, there is a maximum allowed power level which is for free space emission. Yeah? people have decided that at a certain frequency, only so much power is good for you. Yeah. There's also some parts of the spectrum where obviously there's a lot of power in the air. For example, there's this experiment which some of you may have made. You go to a typical broadcast station on a mountain and you put 2 pins in the air. If you do it right, you see the lamp which you connected, you see it just being fed from the amount of power in the air. So if you, for example, radio at 100 megahertz or so broadcast, you can actually take that energy and supply something. This sounds like a crazy physics teacher experiment, but there is a take-home message from that, because many of the medical devices supply themselves from small fractions of the power just in this way. We always know there's some energy in the air, not necessarily harmful, and we grab a certain amount of power to charge a microcapacitor and a microbattery, for example, to have some medical sensor on ourselves without a battery. Yeah, so there's also some use of that. And there's also something where when you can look at microwaves from 2 sides. That's also something which I would like to, which has a very broad application spectrum. So sometimes when you build a micro-based device, you want to do this. Yeah, so for example, if you make an inductor, you're seeing an inductor there. Okay, it's not very surprising that if you coil up a piece of metal that you get an inductor. That's something you have felt before, because the impact of the magnetic field, this is something which is not so problematic. And then we obviously get the function of an inductor. The trouble is that we are also doing this very often in an undesired way. So no matter whether we like it or not, we can say always when we are winding up some kind of wire with a signal on it, and especially for complex systems, this is a problem, then you also do that physically, and then you want to suppress that. Yeah? And for example, this is a bit hitting for effects, but if you have an airbag system, a relatively simple and by now relatively old safety system, though important, you're also doing that. You're coiling up metals, and the problem about the system idea here is that you want to build this to be safe. So you cannot allow the interaction in an undesired way to affect your functioning of the device. And this is what often happens, especially when you put things into packages. Yeah, for example, you put, for environmental reasons, electronics in some kind of resonator, like in the musical instrument. And suddenly certain frequencies are suppressed or allowed. Yeah? And the question is then critically, will the airbag not only work when you have it on the bench, but will it also be working in the specific situation when it's placed in the specific edge of the cockpit or wherever it is? Yeah? So this is what we call electromagnetic compatibility. And this is extremely difficult to achieve, yeah? Because when you look at such a modern Tesla or at such a modern e-car, the amount of electronics combined in your imminent environment is significant. And these systems, they interact, and they still have to perform according to their safety function. Yeah? So what you have to, for example, for an airbag, it's very obvious. You only want to trigger it in the case of the accident, but otherwise not. And this is something which takes a lot of engineering to guarantee. Yeah? So there is, on the one hand, you want to go RF, but because you are dealing with decimeter geometries, you have in front of you a steering wheel and certain volumes where you put electronics in. You have to make sure that in this specific environment, the function is assured. And this is a lot more than just coiling up a piece of metal. And I hope this becomes clear. Then there is, what I also would like to mention is some of the things are obvious. We have data communication, we have mobile communication, but we also by now have a lot of functions where we are starting to rely on, which is where it's not so obvious that you are effectively asking for microwaves. Yeah? So, for example, it's very clear that at the airport you by now have done this. So you have been standing there, and there was this, by the way, 27 gigahertz scanner around you, checking you for weapons or whatever different materials. But there's also by now a lot of ideas just to have that pass by, which sets certain questions about data safety, of course. But for example, the ideal situation for the airport would be you just go through such a portal without having been touched by a person. You just go through, and people could detect any things that you should not take on an airplane. Yeah, so this is these scanners, and that is of course very tricky in doing, because it affects you very personally when when people remove the optically protecting properties of your clothes. What people have not mentioned, and I was a bit surprised to hear, that is navigation. And that is something which is where the devices are getting more and more tricky and more important, because I'm not sure how you navigate these days through a city, but you see a lot of people only going along to the screen instead of watching where they are. And what are they checking? They're checking their position not by localizing them to the buildings, but by relating them to satellites. Because this is what a navigation system is. It is a system which detects faces relative to an environment, be it in the network or more precise on a satellite. That is what GPS essentially is. Yeah? And then the precision, and this is what I'm pointing to, is we are more and more intrigued by this precision we need. Yeah? And for example, there's one thing which you know probably pretty well. Does navigation work in buildings? And why? You could actually argue by now from what you heard already today. Why does navigation not work in this room? Attenuation, very good. Yeah. And what is this room also building? It's attenuating the signals which are coming from. But what is this from the extensions? It's a shield, but it's also a resonator. Yeah, so that's something you can look at buildings from their beauty or from their functionality, but you can simply look at them from the idea of an instrument. So there's a certain number of waves fitting in, and especially, I mean, this is of course then meter waves or 10 meter waves. They would be very low in frequencies, but anything we have in this room, for example, edges like this and also there, you have again geometries which have the length of the waves we are using. And that's why the systems, apart from not having a direct line of sight, they are resonating out these frequencies. So there's no proper service in measuring the phase to the satellite, which is essentially your position. Yeah, so that gives you maybe a better feeling. The next thing is that we talked already about this density of traffic. There's one thing in this which is very critical. Sometimes we need extremely high power. Yeah? And you are maybe you're flying a lot. And the reason why this is possible at all, and especially at the rates we are continuing to do so, is that we have the atmosphere which we are seeing. And what you have to understand at some point is that visibility is not what is guiding traffic these days. It is the availability, for example, on radar. Yeah? So the moment when you don't have proper radar coverage of an airport, you have to close it down. And if the distance is impaired, or let's say the attenuation is getting higher due to the clouds, then you have to reduce the speed at which we are traveling. Yeah? So for example, a normal landing iteration for Frankfurt Airport is something between 55 and 30 seconds per plane. So this is about the landing rep rate when they're coming down. What you learn from the microwaves is, obviously we cannot see through the clouds in the optical domain. For microwave, it's a little bit different. For microwaves, we can still see through the clouds, but the attenuation still changes. And if there's heavy rain, our ability to see is reduced. And so we still get a radar signal. That's the principal idea of radar, that we can see through something, but there's a reduction in the visibility also. It's not lost, but it's reduced. And then we have to shut down or cut the rate at which planes are coming down. This is the reason for something you knew already. If there's bad weather, aircraft are delayed. They're not shut down necessarily, but they are delayed because the airport cannot take the same amounts of planes down which it can at perfect weather. This is something you do already, but this is directly related to the microwave properties of the atmosphere. And what does that have to do now with the devices? It has to do, if I have higher power levels for the radars, I can see farther. Yeah? And it's not surprising to you that for certain radars, which we're using here from Freiburg, we can see up to the maybe to a place like Amsterdam or so, at a certain height, of course, because it's a direct sight. But you need to monitor the airframe. So you can, at certain frequency, you can see the far, but if the weather shuts it down, we are reduced. Yeah? And there you suddenly have a direct relation of a usage and the power level. This is a bit historical, but there is a first mentioning of something which we started to talk about. There is the relation of progress in mobile over time. And the first mobile was a phone. And the data rate of the phone was 0. Not something, 0. And then only after some thinking, people had this strange idea of sending bits over the air. That's quite strange to send bits over the air. And that happened around the 1990s. So that's when you had a data rate of something like 10 bits per second or so. So that is the equivalent of this analog voice. And then you see the expansion of this data rate which you get over time. And when you plot that, whatever you name as a certain data rate, you get an exponential rise, which is the law we are under. We are this for mobile, but we also are under this law for optical and for any data consumption we have. So that's essentially the idea. The mobile communication is advancing in generations. About every 10 years we have a new generation of cell phones, not of cell phones, but of standards, so to say, making sure that this is happening. The frequency range for this is why it's indicated in this way, has not changed. So it was always at the same carrier frequency. So the first cell phone was done in the ranges between 700 megahertz and 2 gigahertz, and up to about 2014 that was the same. There was no change in the carrier frequency where we were doing this. The point I'm trying to make now is what is the new things that you're getting from this network? And this is something where you can learn something also in relation to very principled facts. So the first thing is that with a new generation, we are getting another extension in the number of bits we can send. Again, a certain factor which continues to be exponential over time. Yeah? But what is driving the overall evolution strongly is that that we are not only having a certain number of people on this planet, but the number of connected devices is still exploding. Yeah? So by now, mobile communication is not a network of people speaking, but it's a network of machines, people allowing some people to also to talk. So we have much more machines connected over the network by now than people. Because you can see that very clearly, we are 8 billion people on this planet, and we have about 20 billion active devices. And as we can only use one at a time, it's obvious that this has migrated. You know? And what is also very obvious there is, can somebody explain the term latency? What is latency for you? Maybe you have a proper definition. Where do you observe latency in your life? Yeah. But I try to explain it to somebody, and this is of course a very technical and correct definition. The best I found was, you have a video game and you have something in your hand and you're moving this, maybe to do sports, and the machine is not reacting accordingly. And I'm sure if I gave you 5 devices with a different latency, you would directly point at the nice one. You would have a very clear decision in this room. It is something which is extremely vital for us, because especially for these emotional things, if this is not really doing well, you would say, forget it. We are extremely emotional about that. The reason why we are discussing this for networks is that it's difficult to get that, first thing. But for some cooperative machines, for example, this is quite tricky. So for example, the moment when you are not having a car braking only because somebody is sitting in there, but if you have some remote control of that, for example, a steepler in a machine shop, if this thing is not reacting with a low latency, it will just bump into the wall and crash. So there you get some feeling why it has a very relevant reference, that the data rate we are sending and also the signals we send have to have a low latency, because a robot which would be controlled in this way would not run smoothly, as I'm still capable of lifting this, but it would look like nut, and that would help you to maybe to understand that. And the change now, and that is something which is now really the advances which you're making, that you can ask, why are all these changes, for example, an exponential rise in capacity, possible? And this is a very strange question, which is not easy to answer. One answer is that you're using fundamentally new principles. Yeah. So, for example, there are some things which we know about. For example, if I turn around, I know that somebody is in this room, and if somebody was talking to me, I would even be able to direct and to locate the person. Yeah? If you start to analyze this process, then you realize that it is not only the direct face measurement of a person sitting there and sitting there that I would understand this, but you're starting to learn that if you're detecting the same signal with multiple pixels, like my ears, that would be 2 pixels, then I'm able to navigate, because I'm also getting your signal not on the direct line of sight, but I'm also getting it through the edge reflected, and from you reflected, and maybe also from the top. And I'm mentioning this is because we are using these devices in a quite strange environment. Yeah? So you are moving around at the intake in a lot of structures, and you still are connected. So you have done this. You have used maybe not on all sides of the building, but you have used your cell phone on this side of the building and on this side of the building, while the radio transmitter we are using is somewhere up north in about where I work in Freiburg North. Yeah? And how does the signal directly get to you? It will always get on various ways to you. So you have to make a selection. First of all, which signal do you take from the same path? But that also is a challenge, is a good thing, because if you get the same signal twice or three times, you can use that information. And this is one answer why things like the mobile really work. So you can find out, for example, you could argue there's the transmitter and you're getting the signal around the building, and you're standing behind the building, you're getting it this way. You can say, this is now a double signal, I'm uncertain. You can also, oh, there's a phase difference, and I'm using this system to supply people with service. And if you do this good, you're using a MIMO, multiple input, multiple output, and you can use this to your advantage. And I'm mentioning this because this is the reason why, despite of all the problems in the geometries we have in our natural environment, we still get especially reception. We still can detect weak signals, because when we are moving, if the software is intelligent enough, we can deduce the stronger signal and use that. And if we're realizing, oh, this is not good anymore, we take the other signal which may come in better. And this is why, yeah, so you're applying additional concepts. And then maybe also some other idea, which is from a perspective quite useful. For example, I'm going to use a car in a minute. There's a traffic jam. Yeah? And if you start analyzing the system on a traffic jam, who knows best where the traffic jam is? You could say now the radio and the general service, but if you're really serious, let's assume I'm in the red car, the person who really know are those on the other side who just passed the accident. They have just passed, they exactly know the location of the Stau is, or of the accident is exactly 500 meters from where I'm presently at. So, what do you want now? You can see it from two ways now. You can say they are cooperative. So, if this person just passed the site of the accident and it's friendly, it may give us exactly the position of the problem. So we would know, okay, we are just away from that. Would be a nearly real-time experience. You could also see it from another perspective. When you look at such a traffic situation, in terms of radar, they're all using safety radars. And if this is a non-cooperative setting, this person is using a radar and this person is using a radar. If they are on the same frequency, they would start to disturb each other. And these are the two ways of looking at this situation. If you're looking at a cooperative network, you could gain information, which we're starting to do. So there's car-to-car communication. And if you're not serious, your car by now is running updates. You might have realized that suddenly there's something new on the car, and you didn't really know why is there suddenly an update on my car. Has not been at the manufacturers or at the site somehow, but somehow you have a new update in your car, and this is happening. So there is apparently some communication, and this can also now be used to potentially exchange information. Question is, it's data safety and so on, but it could be useful. The other thing is, of course, when I have a safety feature, I certainly don't want this signal to go into this radar transceiver, because If I'm emitting and receiving at the same frequency, then this might be disturbing my safety system. Yeah? Why is this important? Because both things apply. Yeah? And we make use of the different frequencies in this case. For the communication, we want to communicate with them, we use a lower frequency. And for the radar, we use a higher frequency, because the higher we are in frequency, the higher the attenuation, so that if they are close, the signals could interfere, but the radar signal from this car will maybe not interfere with a distant car more distant than a couple of 100 meters. So that's also where you can make frequency selection to your advantage, that the system is not completely chaotic. Yeah? What is really interesting is when you open such old devices. This is ancient history what we see here. So really, this is 1990s or 1995. So there you can still see components. So this cell phone, I mean, you look at that and say, yeah, this looks really old. It was not even a smartphone. What has come along with that is the extreme miniaturization of the components. And we have done everything in these components apart from making them small to reduce their power consumption. So that is the driving element here, to save. Yeah? And there are two ways to save in this cell phone. And just this is now two secrets why you are surviving this day with your cell phone. The first thing is, this cell phone is a master in switching itself off. Because, for example, when you look at your apps, that is a good example. When you are selecting one app, you are happy. The app is there, it's the right version, it turns up. But what you're not seeing is what is happening in parallel. So if you're choosing a certain app, the principle is everything else is switched off. And that's where you learn something from a system. So you put all these applications, but you switch off. So you could say, I'm selecting an app, but what you're effectively doing is turn everything down, except from what you want. Yeah? This is number one. And the second thing is that we have, based on this optimization, the microwave part, because it needs the connectivity, is still the main provider and consumer in terms of power. How do you know? When you're looking at your screen on your cell phone, you can individually switch off Bluetooth, WLAN, and microwave mobile. Why is that? Because you can physically switch the main consumer off if you don't need it. If you think, I'm in a building, there might be Wi-Fi, I'm switching it on. But if you're going to the open countryside, you definitely will switch off Wi-Fi, yeah? Because there is no Wi-Fi. This is just a reminder, that's also quite old-fashioned. When you look at what is quoted, you will realize we never talk about microwaves. So there's very little information. This is an old commercial. We could take any since then. There was not really mentioning any usage of microwave. So it's something which we use. And maybe somebody can try to explain what has changed in the microwaves over the time. So what were the changes that have been on the radio level in the cell phones? Is there something that occurred to you which was new when you looked at your cell phone? What was new when you got a new one, whatever, a year ago or 5 years ago? Have you observed anything which it's not easy to detect, but there were some changes? That's very good, yeah. And there's one thing which I found helpful because I'm traveling a lot. At some point, you still needed a special phone to go to a certain country. But we are very international here, and I'm sure most of you can use their stuff wherever they are. It's expensive, I concede, but it's at least possible. So this is maybe the real change, because this refers to the microwaves we talked about at this point, because you see this here for the United States. The frequency allocation is very nationalistic. So we, for example, if we use the same distribution for all these services, they will be definitely different in France, just over the border. They have the same ideas, but they have very different. So all these fields which you see, they would move a couple of megahertz aside, because this is a very national concept. And if you're traveling to the US or to India or to China, they will all have similar ideas, but they will always be a remote by a couple of 100 megahertz. And what is quite helpful is that is something where you can learn something. Normally, we would assume that for microwave communication, we need an antenna, which is of course true. But nobody has seen an antenna since, for I would at least say 20 years. Yeah? And this is interesting, because I told you something earlier, which is an idea that an antenna from its size is resonant if the antenna size is similar to the wavelength. That is one way of looking at this. So if you want to build a direct structure related to the wave, then you build something which has exactly that size. But that's not the only way to do it. And that's why you see that here, that in the frame of the cell, of a very early iPhone, this is the antenna. And it's a very special one, because there are different services. So normally you would expect for each service you would have a certain antenna length, because of different frequency. But you can also do it in an integrated way, that you just say, forget this idea about one-to-one and integrate it. And what you're making use of then is that you use again this resonator idea, because this antenna alone will not work. It will, however, consider what is around. So the resonator is a real 3D resonator. And then it's starting to become an antenna. There are some interesting stories. So for example, the real question is, how do you use a cell phone? And when I put up this hand, what is this dielectrically? Why is my hand a problem? What is this, if you just look at it from the physics, if you have to characterize it as me, myself, apart from my personality, what am I dielectrically? A bucket of water. That's what the antenna sees. So this is a glass of water with a structure. And water has two properties. One we already learned about, that is, it has a very high absorption. That's what you can see when you look outside. So water absorbs. And the second thing is that what is the dielectric constant of water? We are on the blue planet, and that's exactly the answer. Dielectric constant of water is 81 in relation to 1 free air. So when I'm touching the cell phone, I'm completely changing the fields around the cell phone, which means the antenna will work and will not work. And that happened actually to Apple in generation 4. They built the cell phone without considering the hand, and it didn't work. So they had the people using it, and the cell phone didn't work, because the hand was shielding the reception of and the working of the antenna. Yeah? So, and why did people realize? Because then the power amplifier was trying to correct that, and the cell phones were within minutes were dead, because it was controlling high power, trying to send something out, was absorbed by the hand, no connection. So there you're seeing that we are in a very complex environment to do this stuff. And what we certainly cannot change, we cannot use the cell phone without a hand. This is something which is, again, a given here. So there you learn the difficulties. Okay. What I already mentioned is this equivalence of power in the digital frame. At the moment, 3% rising. We had 1 to 2. With the new onset, we are getting up. And there's two ways. The one thing is our massive usage of the microwaves, and the second thing is are the data centers in the background. Both are needed, of course, but it's a big, big problem of energy. Yeah. So that's why we are here, to reduce that, and it's mainly on the network side. So these antennas which you see there with the allocated power amplifiers, they're extremely inefficient. We will learn why. And why it's good to make them more efficient, because we need the services, but we also need to get the efficiencies up. Yeah? And this is here. This is exactly what I said about my hand earlier. There are people who are discussing whether the microwaves can be harmful, and they just measured the temperature of the heads without and with microwave radiation, and you can see the effect of somebody foaming. So it is heating. Yeah. But there's also a very simple way out of that. Your cell phone, by now, if you open it, has a simple metal foil, so it's only radiating to one side. So it's not radiating to my head anymore. So it's only radiating there. So that's why most of the time you still get connection. Yeah, and it's, the point is, people make a lot of fuss about this, also about the harmfulness of microwaves. The point being that you have to first critically reduce the amount of power you want. There's good reasons why we want to do that, yeah, because we don't want to emit power which we don't have, yeah, and we need to keep, of course, harmful radiation levels low, which is from various perspectives a good idea. And just as a reminder, the microwave oven is a very cheap device. This is a different one. This is not made from semiconductors. It's the same band, but it's kilowatt level, and this is your homework. Observe the microwave oven and just these resonators which help us to protect ourselves. Yeah? And if you want to protect yourself from this, my first message is clean these protective devices. If there's tomato sauce on the edge, then these resonances do not work anymore. So this is much more important than the other part. And this is something, with this I want to close, the problem of power consumption again. By now with these advanced, we started with these advanced sensor suits for protection. This is a very early one for radar. You can still see this is the problem. By now this is surrounded by at least 10 or 15 radar sensors for very different situations, which also then will trigger the safety measures. And what is the advantage here? The advantage is what are we gaining with this radar? Just also to explain the safety function itself. When you're having an accident, there's always the phase prior to the accident, and you can already line up the protective measures before the accident actually happens. Yeah? And this situation is relatively simple because there it's a relatively small distance. These accidents can be avoided nicely. The problem is always if you have a cross accident. Yeah? So if the airbag, if something is crashing from this side, you have extremely little time. Yeah? And if you then have something which triggered the airbag from this side here, and the airbag is already blown, then injuries can be mitigated much better than for this relatively simple situation. And so there's a lot of things which can be suppressed, which are extremely harmful. Okay. coming to the end. What we will do is in the next lecture, I would like to make some commercials if somebody is interested in also doing this a bit more practically. We're also searching for Hiwis at the moment for some setups. If somebody is interested in this measurement techniques we are talking about here, you can send me an email and apply for that. We search for people at the moment if you have some interest in that. And for the others who do not want to do this, I want to motivate you here for when you're going home now, you have a very broad spectrum of things that you're using in one way or the other, which is this Internet of Things, which we want to understand and make more energy efficient and also more resource oriented, because not everybody can live in such a home. That's just an example, but it gives you nicely the amount of sensors we have both on the medical side but also for convenience. I hope this is interesting to you, and if you stay with us, come back next week, and looking forward to meeting you. Thank you.